Hey folks, I have some examples of torque to share with you, and I've written a couple things down from previous discussion. Uh, to calculate the torque created by a single force, its torque equals R cross F. And by the way, it's R cross F, not F cross R. If you do F cross R, you will get the same magnitude of torque, but you'll get the opposite direction. So you actually need to do these in order, R cross F. And then if you add up all the torques on an object, it makes it angularly accelerate. And so just like Newton's second law is net force equals ma, we have now in rotation net torque equals I alpha. And we just call that Newton's second law in rotation. It's the same thing basically. So the first example, I've drawn it already, is we introduced that in the previous video. We have a rod and we're pulling on it with a force F at an angle, and we're not pulling at the end of the rod. The rod is pivoted at its end though. Okay. So what I want to know is what's the torque acting on the rod and what's the angular acceleration. Okay. So in the previous video, we calculated the torque created by that force. That is equal to d. Now, I did change the variable letter. It's d sine theta, or d sine phi, sorry, times F. So that is your torque created by that force. Now, if that were the only force acting on the rod that's causing it to spin, what would the angular acceleration be of the rod? So I would take my Newton's second law in rotation, I'd solve that for alpha, which is net torque over I, which is that thing we just got, d sine phi times F divided by. So then you have to figure out, hey, what is the moment of inertia of a rod pivoted at its end? Well, previously we figured out that it was 1/3 m L squared. And, pretty much that's your answer. I mean, you can put the 3 up here, but otherwise you're pretty much done. And then, of course, if I gave you numbers, you could plug them in and get an answer for an actual angular acceleration, okay, in radians per second squared. So there's one example. Another example is, let's say I have a wheel that has a rim on it like so. And let's say I'm pulling on the wheel with two forces. We'll call this F1 that way. And let's say there's a string wrapped around this rim and there's an F2 going that way, okay? And I give you the following data. R1, that's this radius here, I'll label it R1, is half a meter. R2, the smaller radius, and notice that I'm drawing both of them perpendicular distance from the axis of rotation to the force. Okay, R2 is 0.2 meters. Let's say both forces are equal in magnitude, and we'll make that an even 10 newtons. We're going to make our math easy on this one. And let's say the moment of inertia of this wheel is somehow measured or otherwise calculated, and it's 1.5 kilogram meters squared. Okay. What is the angular acceleration of the wheel? Okay. Well, the torque caused by force 1 is R1 cross F1, okay, which is 0.5 times 10, which is 5 Newton meters. Now, direction, all right, you have to worry about direction here. So this first force is trying to make the wheel spin clockwise, so I'll put a CW there. Technically, that torque would be into the page, but we'll use clockwise for now. And then torque 2, okay, is 0.2 times 10, which is 2 Newton meters. And which way is that torque? Well, that force is trying to make the wheel spin counterclockwise, so I'll put a CCW for counterclockwise there. So what's our net torque? Well, our net torque, you subtract them because one's clockwise and one's counterclockwise, and you get 3 Newton meters, and the clockwise one is the winner. So that's your net torque. And then if we use net torque equals I alpha, alpha would be that net torque divided by I, which is 3 over 1.5, which is 2, and that would be radians per second squared. So that would be your angular acceleration of that wheel. Okay. So the first two examples were hopefully pretty simple. The next one gets a little more complicated, and I ask a few more questions about it. Okay. So let's say you have a rod, and let's say it's pivoted so that it can swing. Okay. So it's going to, if you let it go, it's going to swing down because gravity is going to swing it down. Okay, so imagine it's like kind of like you're holding a baseball bat at its end, okay, and you're kind of just letting it go while you're holding the end. And so it's going to swing down because of gravity. So I have some questions about this. I want to know what the angular acceleration is of the rod at this moment, when it's horizontal, the moment you let it go, all right? And I want to find the acceleration of the center of mass. Now, it's linear acceleration, just a tangential acceleration, and the acceleration of the end of the rod, okay? Now, these are both, I just want these to tangential. Once the rod begins moving, there's also going to be a radial acceleration. Right now, I'm not concerned with that. I also want to find the force of the pivot. In other words, you're holding this thing right here. If you have to hold it up a little bit. If you don't hold it up, the whole rod would just drop straight down like this. Okay, so that's not exciting. So we have to supply some upward force here. That's your FP I'm looking for in order to make the rod actually spin. So what is that force? Okay, in terms of the givens. Oh, and the two things we're going to give you besides this is the mass of the rod is M and the length of the rod is L. It is pivoted at its end and is a uniform rod. Okay. Well, in order to do this, your first step would be to draw an FBD because now we have multiple forces acting on the rod. Okay, and as I mentioned, we're going to have a force up. That's force P. Okay. The only other force acting on the rod is gravity. And you always put gravity at the center of mass of the object, whatever that object is. So the center of mass is where you put that force. You can pretend all the weight of the object is at that one point. All right. Now it's spinning about this axis. So we're going to do net torque equals I alpha. All right. Now, there are two forces acting on the rod. There's FP and there's FG. FP doesn't cause any torque because FP acts through the axis. In other words, there's no radius there. So I'm going to ignore that one and look at FG. So we have R, which would be, what's the radius from the pivot to the center of mass? Well, that's L over 2 times the force of gravity, which would be mg. So that's your torque. It is clockwise, and that's the only torque acting that's making this thing spin, so I'll just stick with that. What's the moment of inertia of the rod about its end? Well, that's 1/3 ml squared. And then we're going to solve for alpha. So that's pretty much it. You got to do some canceling here. So like the m's drop out. Hey, it doesn't matter if it's a lead rod or a wooden rod. It's going to have the same angular acceleration. One of the l's drops out. And you end up with g over 2 equals L over 3 alpha, or alpha equals 3g over 2L. Okay, so that's your angular acceleration at that moment. Now do notice it does depend on L. So the longer the rod is, the slower this thing will accelerate. The longer it'll take to, let's say, get the vertical. All right. Now, so we found the angular acceleration of the rod. That's the same everywhere along the rod. Okay. What about the tangential acceleration? So in other words, the center of mass has a tangential acceleration, and the end of the rod has a tangential acceleration. What are those? Well, you might recall from earlier in this chapter, tangential acceleration simply equals R alpha. So the tangential acceleration of the center of mass, okay, equals R, which is how far is it from the pivot to the center of mass? Well, that's L over 2. And then we have alpha, which is 3g over 2L. And if you do this, you notice the L's drop out, and you end up with 3/4 g. Okay, so that point, the center of mass of the rod is accelerating down at this moment, accelerating down at 3/4 g. Okay, what about the end of the rod? All right, well, the tangential acceleration of the end of the rod is the same equation. It's the same alpha. Every part of the rod has the same angular acceleration, but they have different linear accelerations because they have different radii. Well, how far is it from the pivot to the end of the rod? Well, that's just L, and then times 3g over 2L, and you end up with 3/2 g. Now notice that's bigger than gravity. It's 14.7. That means this acceleration, believe it or not, is more than gravity. Okay, so if you were to hold like your pencil in the end of your pencil in your hand and let it go, the tip of the pencil that's farthest from your hand actually has a downward acceleration that's more than 9.8. Okay, So now we found this and this. Now what about force on the pivot? Okay, well, for that, okay, we're going to do net force equals MA. Now, here's the problem here. Every part of the rod has a different tangential acceleration. Hey, we just found two different ones right there. Okay, so what A do you put in here? Well, it turns out whenever you use Newton's second law, you always use the tangential acceleration of the center of mass. And also for this problem, I'm going to just say down is positive. Okay, so I'm going to put a little down arrow on my chart here and say down is positive. Otherwise, you'd get a negative acceleration, which would be fine, but I know it's down, so I'm going to say down is positive. So in this system, I have two forces. I have Fg down and Fp up. So we go Fg minus Fp equals m times A of the center of mass. Well, this turns out to be pretty easy. This is mg minus Fp equals m, and the acceleration of the center of mass, we had 3/4 g. Okay, so if you solve for Fp, you get mg minus 3/4 mg. You get 1/4 of the weight, 1/4 mg. Okay, so that's the upward force you have to exert on the rod to get it to spin like this. So if the rod weighed 2 pounds, Fp would be up at a half pound. That'd be 1/4 of 2. Okay. Now, one last twist I want to put on this problem. Let's say the bar is now rotated some. So now it is here, let's say. And it's rotating clockwise. And I want to find the angular acceleration now. Okay. Well, gravity now acts, it still acts downward, but now it's at an angle to the rod. This is phi, which I hope you would agree is going to equal that angle there. Okay. And if I do net torque equals I alpha, okay. Now remember, there's still an Fp. Now Fp at this point is going to kind of go up at an angle like that. I'm not going to worry about that right now. And you still have Fg acting straight down. Okay. So our torque would be force of gravity, which is mg. Now in this case, you could either look for how much of gravity is perpendicular to that rod, or if you imagine your line of force, find out how much of the rod is perpendicular to that line of gravity. It doesn't matter. In this case, they're probably both about the same amount of work. I'm going to find that length. That's my perpendicular lever arm. Well, that's just L over 2 sine of phi. So this becomes L over 2 sine of phi. Okay. Oh, wait, I take that back. It's not sine. Hopefully you caught my mistake. All right. That is cosine of phi. Okay, the length of this is the adjacent leg is cosine of phi. And that equals I, which is 1/3 ml squared times alpha. Okay, so you'll notice the m still drop out, and one of the L's still drops out, and you get g over 2 cosine of phi equals L over 3 alpha, or alpha equals 3g over 2L. And the only difference between this and the last one is you have a cosine theta. So if you look at the last answer, we had a 3g over 2L. Well, now you have a 3g over 2L times cosine theta. Now, does that make sense? Well, think of it this way. When the bar is vertical at that moment and it's swinging, okay, at that point, it's reached its max angular velocity. It's no longer accelerating. So alpha should be 0. Well, at that point, what's your angle? Well, it's 90 degrees. What's cosine of 90? Add 0. So that means alpha would be 0 down there. So that's a way to kind of check to make sure if you have the sine or the cosine right. All right. So I hope you found that video helpful, and thank you.